Hello, everyone. My name is Nathan Peck. Happy to be able to chat with you all today about building a SaaS on AWS Fargate. Now, I have a long history of building SaaSes. I actually started out in the software industry, working for several different SaaS startups, and unfortunately, they all failed. Fortunately, I learned some things from that, both from trying to build my own SaaS as well as working for different SaaS startups. I took a little break to work in social media for a bit, and then I came back to work at Amazon, which obviously has some incredibly large SaaS offerings. And today, I'm going to share some of the learnings that I've had over the years about building, and specifically building SaaSes with containers on AWS infrastructure, and with AWS Fargate as the compute layer for running that infrastructure. So the way I decided to organize this talk is all about building trust with customers, because I feel like trust with customers is key for the success of a software as a service. Whether you're a startup, whether you're a large enterprise, whether you've been in the SaaS space for many years or are just starting out. And there's 4 key pillars to building that trust. The first being that I trust your software to be available when I need it. Second, I trust your software to keep my data secure. Thirdly, I trust your software to get new features that I need. And fourth, I trust your business to actually be here for the long term. So I'm going to start out talking about that idea of I trust your software to be available when I need it. And this is super important because if you're building a service that people are paying for and they're paying money to use it, they're going to expect it to be online anytime that they need to use it. This isn't like a social media. It can go down. It can have some fairly significant downtime. And nobody really cares because they're getting that service for free. They'll complain, but they'll still come back, even though the social media had a downtime. SaaS is completely different from that. They're paying money. You have downtime. A lot of times they'll cancel their subscription because they didn't get their money's worth. Now, when we think about availability, one of the ideas that I formed from working at different SaaS companies, including Amazon, is this idea that availability is not a binary, it's a spectrum. So we can go all the way from the extreme of availability where everything is down, nothing is working at all. You try to load up the website or use the application and absolutely no feature of it works, over to everything being functioning perfectly. And I load up the website, it loads up quickly, all the features work. But realistically, especially in a large company like Amazon Web Services, which has a ridiculous number of offerings out there and a ridiculous number of APIs, it's never all the way over on the right-hand side. There's always something broken somewhere. And most of the time, you wouldn't even notice that, right? There's ways to achieve that such that you actually can minimize the impact of downtime and availability events. Now, it's super important to consider how you minimize downtime impact, and there's a lot of different factors to consider. With any service that has a lot of different tenants on it, you have to consider which people are on a free tier, which people are low budget spenders versus really high budget spenders. What's the level of the workload that they're running? Very small, very large. And when I'm trying to minimize the impact of downtime, I also have to start thinking about problems like the different resources that are being shared between tenants. Whether there's a noisy neighbor that could be causing actually an availability event for other tenants that are co-located with that particular customer. And then last but not least, we have these unpredictable activity patterns and challenging scaling policies. So how do we get around all of these problems at the infrastructure level? And the key to that is isolation. So isolation allows one part of your system to stay up and available while another part is unavailable. And the goal is that you can actually have customers whose trust is going up in you and in your system, even while another customer, maybe a few customers, are experiencing a downtime and their trust is going down. But overall, your overall trust across your customer base could still be rising, even though some of your customers are being impacted. And so this gets down to one of the key differences between monolithic applications and applications that are made up out of a variety of different services. There's a trend right now sort of away from microservices back to monolithic applications. And it's understandable why that is taking place, because microservices got a little bit crazy there for a bit. People were doing too many microservices. They were doing too small of microservices and creating these really complex architectures that tended to fail just due to their complexity. But I think that there's a balance point. There's a balance point between building an entire monolith which goes down all at once and all of your customers lose trust in you versus building a system out of smaller services which are properly segmented such that one of them can go down while the others stay available. Now, it's important also to think, as we talk about isolation, by how you isolate new code. So there was a recent report put out, I was actually just reading about it this morning, where they found that the biggest impact now to the rate of being able to develop code is actually not writing lines of code. We have generative AI for that now. We have very experienced people writing code. But it's actually the change failure rate, which is how much the change that you're making on a system introduces new bugs and problems and downtime and failures of different services in your system. So isolating new code during deployments is incredibly important. And container orchestration systems such as Amazon Elastic Container Service have this built in to the core concept of the platform. I see a lot of people who start out with container orchestration, they maybe start out with the easy, basic way of doing things, which is I just push all of my containers to the latest tag on my container registry, and I just restart the service, and I always run whatever the latest version of my container is. But this is not the way container orchestration is designed to be used. Container images can be versioned, and the task definition, which is the core concept grouping the deployments inside of Amazon ECS, is also a versioned resource. And so the way this works is you can have multiple versions of the task definition, and you use an Amazon ECS update service API call to tell Amazon ECS to roll out a new version of the task definition with a new version of the container to your service. And so Amazon ECS is designed to allow you to roll out this update with this new code while ensuring there's zero downtime. And it does this in the following way. You'll see, for example, there's an Elastic Load Balancer with 3 copies of the application task behind it. And initially, all 3 of these are version 1. But we want to migrate from version 1 to version 2. Maybe version 2 has a new feature, some sort of performance change or bug fix. So the way Amazon ECS avoids dropping traffic is it launches another parallel copy of the tasks with a new version in parallel with the old one. And then it starts gradually draining traffic off of the old task and shifting it over to the new task. This all happens behind the scenes automatically through the load balancer integration. And it's smart. So if it sees, for example, that while it's in the process of doing this shift of traffic from the old task to the new task, it sees that one of the tasks starts failing health checks, maybe it goes ahead and crashes, or a new feature that was actually launched not too long ago, one of your metrics in CloudWatch actually starts to spike. Maybe its response time goes up, or maybe even the rate of, let's say, 4xx errors, validation errors goes up. It will actually catch that and have the ability to roll back automatically to the previous version of your task definition. So this is one way that you can isolate new code. You want to roll it out in such a way that traffic gradually shifts over to it, and if there's any problem that's located or noticed by the orchestration system during the process of that rollout, it'll be able to roll back instantly to the previous version. Because it's not going to shut down any of those previous version tasks until the new ones are all up and healthy, and they've had a certain amount of bake time in terms of staying healthy for at least a minute or 2. Now, for a large SaaS, you're inevitably going to have different tiers of user, and they're going to have different levels of requirement for their infrastructure. So here we see a basic tiered tenant. Maybe these are free tier. They are all using a shared pool infrastructure. So think of this as one instance of your task that's being, or one instance of your application that's being used to serve maybe hundreds or even thousands of connected tenants. And they're all sharing the resources of that application. And all of the requests that they're making, whether they be web page requests or API requests, are all being served out of the same shared pool of compute resources. On the far end of the spectrum, we have premium tiered clients. These tend to be extremely large tenants who require their own dedicated infrastructure perhaps due to security reasons, or just the fact that they're paying a lot more money than a basic or advanced tier. they want to be on their own dedicated infrastructure. And so for them, they would have a fully provisioned, dedicated stack of services that's just for them. In the middle, advanced tier, maybe these are mid-tier paying customers. They're not paying the most premium price. They're also not free tier. You might have some components of your overall SaaS system that are shared tenancy, and some that are dedicated to specific tenants. Mostly around data storage would be the ones that we have as dedicated. Now, we can actually get even more granular than this. So this would be 3 different levels of isolation. We can get down to isolating one of these pools as well. So this is infrastructure that Amazon uses extensively. Every service I've worked on at AWS for the past almost 8 years has used cellular architecture. And it's super important because this allows you to minimize the downtime impact when a particular cell fails. So here you see that there's not just one production deployment. There's actually 3, production 1, 2, and 3. In many cases, some of the large services that I've worked on, they've had 20, 40, maybe even hundreds of cells across which customers are distributed. And the idea is that if one of the cells fails, only the percentage of customers that are in that cell are going to see an impact. So in this case, with 3 cells, there's a 33% impact rate. But even though that seems pretty high, that still means that 66%, or the majority of your customers, could still be having a good trust-building experience with your service, even though 33% of them experience a failure. So a little behind the scenes magic, lifting back the sort of curtain a little bit. A lot of times you'll see outage notifications from AWS, and you'll see on social media people saying, oh, AWS is down. I tried to hit the Amazon API, AWS API, and I've received a failure. And then you'll see other people say, it worked for me, like I didn't notice anything. It's usually because of the cellular architecture. Maybe one cell had a failure of some type, but other cells were not impacted. So within a cell, though, you still have the noisy neighbor problem. And so this is challenging because different tenants have different usage patterns. So you might have one tenant that has an extremely high request volume, whereas another one has a low request volume. You may also have a tenant whose workload just requires 100 times more compute for some reason. Maybe whereas the other tenants are sending 1 megabyte files, this tenant occasionally drops in a 100 gigabyte file, for example. And then you have tenants who will have a normal request volume to your service, but then out of nowhere they'll suddenly spike to 10, 100, 1,000 times. So how do we deal with this? How do we prevent spiky tenants or tenants that just blow up out of nowhere for some reason from impacting other tenants for a SaaS system? The key to that is throttling. And not just one layer of throttling, but we're talking about 3 layers here. So throttling by activity type, throttling by compute consumption, and throttling at the underlying resources. The way that I like to throttle first and foremost is using serverless throttling at the front door. And you'll see this implemented across a lot of Amazon services. You'll see that there's a quota. There's even a whole quota console that you can use to explore the quotas that are available to you. And every AWS service tends to have a rate at which you can call it, and then a refresh rate at which your token bucket refills with tokens that allow you to continue to call this service. So for example, inside of Amazon API Gateway, you can set up a custom authorizer which can tell per tenant who that tenant is, and then based on the identity of that tenant, it starts to consume tokens at a given rate based on the API requests that they make. And so here you see on the upper right-hand side, there's a rate set on this API of 50 requests per second, a burst of 50, and a quota of only 1,000 requests per day. So this might be one way that we limit a free basic tier user from abusing the system or suddenly blowing up its usage with a bunch of heavy resource calls. Behind the API sort of quota and throttling, we also want to throttle the amount of resources that individual services can actually consume. In the old days, when I first started building SaaS, it was common to have just like a PHP process on the server, something like that. And all of these different tenants were spinning up PHP processes in the background whenever they made requests. And all these processes were running on the same shared architecture. And this was problematic because it left it up to the operating system as how it wanted to distribute the CPU resources or memory resources. So you could have one tenant who suddenly spikes their utilization and starts consuming a bunch of CPU and a bunch of memory, and actually starves all the other tenants on that box of resources that they would need in order to do their job. And so I fought this many times over the years in the early days with these PHP services. Containers help solve this. So one of the beautiful things about containers is you can set CPU and memory limits per container based on how much CPU and memory you want a particular tenant who's being served by that container to be able to consume. And it can get quite granular. With AWS Fargate in particular, since we're talking about that in this talk, you can get all the way down to 1/4 of a CPU and 1 GB of memory. And so that will allow you to serve, for example, 4 tenants per CPU if you wanted to give each tenant their own process. Perhaps you want to group tenants inside of a process, but that would still allow you to segment 1/4 CPU intervals from each other, such that tenants that are being served by 1/4 of a CPU don't have the ability to take CPU away from other tenants. And the thing that powers us behind the scenes inside AWS Fargate is micro VMs. So AWS Fargate actually launches every single container task in its own isolated micro VM that's just the size that you specified for that task. And this allows you to extremely limit the amount of impact of a spiky customer. So here, for example, you see there's not only a cellular architecture here, there's 2 cells, production 0 and production 1, but there's also different containers within that cell. And you can see that, for example, in production 0, all of the customers in that cell are clearly making very high utilization of the service because we've reached 95, 95, 95, 99%. So this could be problematic. We could see a slowdown in production cell 0, but it wouldn't have the ability to impact any of the other cells. In the right-hand side on production 1, you see that the different tasks within that cell are kept separate from each other. And so perhaps one tenant who was making use of one service inside one of the containers is able to spike it up to 95% CPU utilization, but those other containers are unaffected by that. You see them chugging along at 25%, 65%, which should be more than enough for a very high quality service. So hopefully this gives you an idea of how you might be able to use containers, AWS Fargate, and Amazon ECS clusters to segment your architecture and isolate it. Don't forget to make use of those rolling deployments. But let's move on to the next pillar of trust, which is keeping data secure. This is super important because if I'm paying for a service and my data leaks, I might even be opening myself up for litigation as the SaaS owner. Like it could be pretty bad, right? So once again, microservices are a key pillar of security isolation. And the advantage of microservices is that you can start to build different portions of your system that have limited access to specific types of data, but they don't have access to all of the data in your system. This allows you to minimize the impact of a vulnerability. Let's say that one of your services is able to get hacked. Somebody manages to break through all of your layers of security and get the worst possible thing, remote code execution, inside one of your containers. Now, obviously, this is a dire situation, but what could you do to actually limit the amount of impact that this hacker has, even though they're already in your system and they have a shell open and they can run any command? Well, let's talk about that. So first of all, when you're running microservices, you need a firewall to protect them from bad internet traffic. So this is something that Amazon ECS and AWS Fargate support. Out of the box, they support Amazon VPC, Virtual Private Cloud, as a core concept. And what this allows you to do is each of the tasks, each of the containers that are running inside of your cluster has its own network interface inside of your VPC, and that means it has its own IP address, and it can have its own security groups. So what that allows you to do is you can build these really granular access controls between everything that you are running. So here, for example, in this case, we see that web users are allowed to talk to your public-facing application load balancer, which is serving as an ingress for internet traffic from your website or from your application. And that load balancer is allowed to talk to the Elastic Network interface for one of your tasks. Maybe this is your website task. It's the one that does a server-side rendering of your web pages and returns them back to the browser. Now, the network interface for the website task is also allowed to talk to another task. But you'll see that traffic is actually denied from the load balancer to that other task, and that other task is not allowed to talk to the website. So what could this other task be? Maybe it could be an API, something where the website, as part of doing the server-side rendering, it needs to fetch some data from the API. But there's no reason why this internal API should ever be talked to by the public internet, and it shouldn't be talked to by the load balancer. And there's also no reason why this particular back-end internal service should ever be talking to the website. So here, we've been able to build out this granular access control and these granular ingress rules that are not only protecting against external traffic, but internal, they're directional, so that you can control which services are allowed to talk to which other services. Now, if you've been using AWS for a while, you're probably familiar with IAM rules. This is how you give a thing that you're running, or a thing that is interacting with the AWS account, a permission which it can use to call AWS APIs. And this can get extremely granular. Traditionally, when I was running things on an EC2 instance early on in my career, there was only one option at that time, which was really to give the EC2 instance a role. And the problem was then if I'm running 10, 15 different services on an EC2 instance, then the role that is attached to that instance becomes like a superset of everything that's running on that instance. So let's say I have a web task and an API task. The web task needs to talk to the S3 bucket, and the API task needs to talk to a DynamoDB table. Where if I was running on a bare EC2 instance, I just have to give that EC2 instance permissions to talk to both the bucket and the DynamoDB table. But that's problematic because if someone gets into the EC2 instance and has remote code execution, now they can access every single resource that particular EC2 instance has the ability to talk to. Containers and Amazon ECS roles allow you to limit that. So with containers, my web task running as one container has its own IAM role, which allows it to talk to the S3 bucket. And the API task has its own IAM role that allows it to talk to DynamoDB, but they don't see each other's roles. This adds another layer of protection. Even if somebody was to get remote code execution into one of my tasks, they would then have to do a container breakout to get out onto the host system, and then from there get into another container in order to access its IAM role. So you're going to see a lot of isolation there. And in the case of AWS Fargate, if I'm running these things as separate tasks that are in their own separate VMs, there's no risk of the container breakout either because the micro VMs are extremely well isolated from each other. So one of my particular tasks could be completely owned. The hacker got in, they got remote code execution, they can do anything they want inside that task. But my other tasks that are running in AWS Fargate are absolutely isolated, and their IAM rules are secret and kept separate, which means that the resources that they have permission to talk to are also protected. Now, that's separation of security at the application layer. But let's start talking about tenant data as well. So earlier we talked about pools of infrastructure. Well, data could also be pooled. Here's 3 different levels of separating tenant data. In the first, you see an orders table. This would maybe contain data for every single tenant in your system. And there's just one table for everybody that you serve in the SaaS. Level 2 is cellular architecture again. You'll see a cell table for each cell. And then level 3 is a premium tier client where that client actually has their own dedicated table and nobody else's data is actually in that table. So let's talk about how we can protect this data using this understanding of the 3 different tiers. All right, here's a piece of code here. Unfortunately, this code is horribly vulnerable. They forgot to add a validation here that the user ID being fetched is actually a member of a particular tenant organization. So here in this case, evil user Eve is able to enter a request for orders/Alice and try to fetch Alice's orders and see her orders, even though Alice is potentially belonging to an entirely different organization, a different tenant entirely that you're being served as the SaaS. So this is extremely problematic. If this was to come to light, then Alice and her entire organization would lose a lot of trust because somebody in a different organization was actually able to access their data and get it out. That's a huge deal breaker. How do we fix that? This diagram looks incredibly complicated. It looks a little scary. There's a lot of moving parts there, but I'm going to talk about it at a high level, what this is doing, because this is how Amazon actually protects your data and does multi-tenant isolation. So when requests come in, there's obviously an identity attached to that request. Amazon Cognito User Pool is one way that you could store these identities and validate them. So as part of validating it, we're going to authorize that identity and pass that through into Amazon API Gateway. Amazon API Gateway is then going to use its knowledge of who the identity of this user is, and it's going to use that to take the normal role that would be given to this particular application and actually downscope to another IAM role that has reduced permissions for the duration of the request that's being served. So earlier I talked about how, for example, an API deployment, an API container could have a particular IAM role that gives it access to a DynamoDB table. Well, we could get a lot more granular than that. So here's an example. Amazon ECS task role. This is a super high level IAM role, which allows the DynamoDB query action on the entire orders table. So this allows you to fetch anything you want from the orders table. However, you'll see a tenant scoped role is a little bit more restrictive. It actually has a condition on it which says, I'm going to look to make sure that for all values being fetched, the key actually starts with the string Acme, which is the name of a particular tenant organization. So here's how that would look in the code. You'll see the code looks very similar. And believe it or not, this code actually is still vulnerable. It does absolutely no validation as to whether or not a user ID is part of a particular tenant organization. However, due to the fact that we implemented in one place at the upfront that token vending machine, which downscopes the role, this code is actually secure. And the reason why is because when the data is looked up out of the database, the only way to look it up is by specifying a tenant ID and an order lookup. And that tenant ID is being validated by the IAM role. So even though this code is vulnerable, it has the exact same vulnerability, when Eve tries to fetch data out of the database, she's able to get the code to generate the right query to fetch Alice's data, and it goes all the way through to the DynamoDB layer, but then DynamoDB actually rejects the request because it sees that Alice is not part of Acme org, and Alice's org, which she can't change, is part of the token vending machine, blocks her from actually fetching Eve's data. So this type of approach is incredibly useful because as programmers, we all make mistakes, and there's probably numerous queries and endpoints in a large SaaS system, and it's very easy to forget to add a validation on one of them. And when we forget to add that validation, you need another layer to protect against. And so in this case, this is showing how you can use an IAM identity that's been downscoped for the duration of a request to stop attackers from being able to fetch data that they're not allowed to fetch. But what happens if the attacker does get through? They're able to trick the system into doing some sort of lookup, fetching data for another user. Well, container orchestration with AWS Fargate and Amazon ECS can actually still help you with that. Amazon ECS Firelens is going to help you audit everything that goes on in your system. So here we see Eve's evil request, where she tried to fetch the orders from Alice. And you'll see that due to the fact that we had that validation that we built, it actually returned a 401 status code, so that's good. But what this allows us to do with the auditing is we're able to see the identities here. So we're able to see that there was a 401 generated. It was for this particular resource and who generated Eve. And we're like, okay, wait a minute. Eve is an evil user whose only reason why they're using our SaaS right now is they're trying to figure out how to hack into somebody else's system and get their data. Let's ban this user. Let's get them out of here, right? So think about setting up Amazon ECS Firelens, because one of the things I love about it is it allows you to attach metadata to your logs and then query that data. So I'm able to see here some custom data such as tenant ID. I'm able to see ECS metadata. So what cluster, what cell, was actually serving this request, as well as the particular version, the task definition there, and the task ARN that was actually serving that request. So I have all the data necessary to determine if an attacker was attacking the system, what they did, and what they tried to do. All right, let's move on to pillar number 3. Pillar number 3 is that I trust your software will get new features that I need. This is super important for any SaaS because customers who are paying, they demand velocity on development. There's generally not just one vendor out there offering particular services. There's more than one. And customers tend to compare services based on whether or not they're getting new features. If you see a particular service that's kind of dead in the water, it's not getting anything new, you start to wonder, why would I be using this and not using a competing service that has a lot more velocity, has a lot more features being built? How can we maintain trust with the ability to build features? Well, let's talk at a high level about some of the philosophy behind this. And the philosophy being that the less overhead you have, the more time you'll have to build features. So here we see 2 developers. There's certain things that developers need to do as part of their day-to-day jobs, such as learning, maintenance, and implementing features. And one of the unfortunate realities of a lot of software development organizations out there is that as you try to implement features, some of these other parts of the pie chart get sacrificed. A lot of times the learning part gets sacrificed. You'll have an organization that's doing major crunch time, and software developers just aren't able to keep up on the learning front. They're not able to keep modern with their skills. And next thing you know, your organization as a whole is using old technologies, doesn't have anybody who knows the latest and greatest new things, and all your best developers who want to learn and want to keep learning have actually left. They've gone to the competition, so there's major brain drain. So we got to maintain the learning part of that pie chart, right? The implementing of features, that's important for staying competitive with other SaaSes out there. So what's the one part of that pie chart where we can try to sacrifice things? That's maintenance. But if you sacrifice maintenance in the wrong way, you end up with instability of your system. You end up with old versions of things, vulnerable versions of things, and a system that's going to fall apart at any moment. So how do we balance all of this? Like we want everything, but we still want to kind of have more feature development, maintain the learning, maintain the developer happiness, while also reducing the maintenance. Well, we have to start thinking about how to build things in such a way that maintenance weight doesn't increase as you build more. So typically, you see a little stair step there. The pink stair step is showing feature development. As the system gets more complicated, it gets more features, people are building more, there's more to the system to maintain. And unfortunately, that generally means that the maintenance burden goes up exponentially. We want to get away from that. We want to get to something where there's initial setup burden. We set up the system, then as we build more features, the maintenance burden levels out logarithmically and it kind of flattens, and we're able to keep this thing going without an ongoing growth in the maintenance burden. AWS Fargate is a great tool for that. So AWS Fargate, it takes away a lot of the maintenance burden that you would need to do traditionally with a container orchestration system. You'll see that there's patches to the operating system, updates to the Amazon ECS agent. This is typical. Every operating system requires patches. Every piece of software requires patches. There's also the number of EC2 instances that need to be run behind the scenes, as well as the generation of EC2 instances that need to be managed. So every reInvent, typically, AWS comes out with a new instance that's faster and cheaper. So you got to keep up with whatever the latest and greatest architecture infrastructure is. And then last but not least, there's the patches to your container, so your actual code inside. Maybe there's a vulnerability that's discovered inside one of the packages that you depend upon, or a vulnerability in your actual runtime that need to be patched. So ideally, we want to move away from the EC2 model where you have to manage all of that, over to AWS Fargate, because it means you don't have to manage anything at all except for your code and the contents of your container, and that any vulnerabilities or patches need to be done against your own code. So this means developers' time is freed up from a lot of that maintenance burden. They're able to spend that on developing features and making the code better for the application itself. Now, there's also a lot of ways to reduce the initial setup burden as well. So setting up Amazon ECS can be a little bit challenging. It's a little bit complicated, like any container orchestration system. But you'll see that there's pre-built patterns. I highly recommend checking out AWS Cloud Development Kit if you haven't yet. It's a tool that gives developers the ability to provision their infrastructure using their favorite programming language. Developers generally like to stay in their programming language, trying to learn how to deploy infrastructure using YAML or CloudFormation or Terraform. It's a different programming language. It's a different thing to learn. But with this system, you're able to learn using these APIs that are written inside of a programming language, in this case, JavaScript. So if I was a JavaScript developer, I could actually use this TypeScript, JavaScript, very familiar pattern to deploy an application load balanced Fargate service. There's a pre-built pattern that we've built called AWS CDK Containers ECS Service Extensions that I particularly like because it gives you this modular system to build custom-built programming extensions that you can chain together to build out the infrastructure that you want. So here you can see you're using this this name description is an instance of a service description, which is essentially a task definition. And we're adding on different extensions. Each of these could have been developed by one of the programmers in your side of your organization and actually shared within the software organization as a tool that you can plug into your infrastructure. So this allows all the devs who are working on infrastructure to collaborate with each other and actually share infrastructure patterns in a way that is very familiar through their Git interface and through whatever internal code sharing platform that you're using. But you don't have people reinventing the wheel and building infrastructure from scratch every single time they want to deploy. Now, let's talk about the last pillar, and that is I trust your business to be here for the long term. This may be the most challenging of them all. and there's many factors of this. Not all of these can be solved just by the cloud provider and the services that the cloud provider offers. But generally speaking, there's many different ways that a SaaS can run out of money and die. Obviously, there's the expenses of marketing, there's expenses of developers. So if we're able to reduce that maintenance burden, as I mentioned earlier, maybe that makes the development and the maintenance burden a little bit cheaper. I want to talk about the infrastructure burden now, though, because that's something else which can balloon over time and kill a SaaS. So the dream of building a SaaS is that you're going to have cost, scale, and performance and tenant consumptions always staying in sync. So as I acquire more customers, more tenants, and those grow over time, or maybe even decline over time, some people churn out, the cost, scale, and performance is going to stay in sync. And so we're going to keep a slight margin, right? So that gap in between the two lines is the profit margin. And so hopefully as the number of tenants go up, we keep those two lines in sync with each other and we can start making more and more money because that chunk of the percentage margin grows over time. But this is the dream. The reality is a little bit more complicated. So generally speaking, once again, we have different tiers of user. You have the most number of basic tier users. So here you see catalog size, the one salmon pink on the bottom. That is the number of customers of that particular tier. You'll see that basic tier is quite large. There's a lot of free tier users. Everybody wants to use something for free. The advanced tier, the people who are paying the most premium price, there's going to be fewer of them always. There's only so many people who can afford to pay the big bucks for the SaaS. However, the unfortunate thing is that the infrastructure costs for those basic tier users could actually end up being blown way out of proportion compared to the infrastructure costs for the advanced tier users in such a way that the tenant revenue is so small that those advanced tier users are barely managing to pay for all the basic tier users that are part of the system. So this SaaS is completely out of whack. And next thing you know, you maybe end up losing one of those advanced tier users and the entire stability of the SaaS is broken such that now it's churning through money. It's losing money rather rapidly. So it's important to think about the margin for a service, not just at the top level of what's the in and out burn rate of this the software development and engineering organization as a whole, but rather we got to look at the margin of every single tenant that is actually connected to the system and consider the resources that they are using relative to the amount that we're charging a particular tenant. So what this allows you to do is determine whether there's something that's out of balance in the pricing model and the implementation of the features that are being offered to tenants. You might be surprised to find that some features are dramatically more expensive to offer than others. Maybe generative AI is one of them, right? You could add a generative AI feature to your service, and it's fantastic. Everybody loves it, but it turns out that it costs a lot more to offer than you're actually charging, and so suddenly all those basic tier users who are using that generative AI feature are consuming too much money. So let's look at the infrastructure costs here. Here we have these cells again, and the cells and then the containers within them are each tracking how much resources are actually being consumed as tenants use the system. And so we got to look at these tenant utilization at the lowest level, at the container level, and see what requests that they're making against that container relative to the consumption of resources by that container. Here's how you can start to set that up. So AWS Fargate produces, through Amazon ECS, a constant stream of telemetry. And this telemetry is not just your application logs, like I talked about earlier with Amazon FireLens. FireLens, that's taking your application logs and sending them off. But there's also container insights and Amazon EventBridge. And what this allows you to do is capture the actual raw underlying events that Amazon ECS produced as it harvested information, telemetry information out of this container. So here's what that looks like. Here's an example event that's coming out, and you're seeing all these stats that are being captured as I run this sample task, which is actually just StressNG. It's a generic like performance testing benchmark tool. But you're able to take all of that, put into CloudWatch, then use CloudWatch log insights to crunch all the numbers and find places where there is an unusually high amount of consumption by a particular tenant or by a particular service inside your cluster, or even by a particular cell in your overall infrastructure. So take a note of that URL there, because there's infrastructure as code for deploying a dashboard which will take your raw CloudWatch log insights telemetry and crunch all the numbers and give you a report on where your biggest cost savings potential lies. Now, it's important to understand, because this session is about AWS Fargate, that there's a difference between EC2 pricing model and AWS Fargate pricing model. So when you spin up an EC2 instance, you're paying for the capacity that EC2 instance has, whether or not containers are actually running on that EC2 instance. So if I spin up a giant EC2 instance with 16 cores and 64 gigabytes of memory, I'm paying for that thing the entire time that I'm running it. Versus AWS Fargate, you're paying a slightly higher price for each CPU core and each gigabyte of memory compared to the EC2 pricing, but you stop paying whenever a container stops. So here you see on the bottom, sometimes I'm running 3 containers, sometimes I'm running 2, sometimes I'm running 1. Well, that sort of empty space above the containers is my cost savings compared to paying for EC2. With EC2, I would have paid for all of that, whether or not I was using it. With AWS Fargate, I'm only paying for what I use as long as I'm using it. But it actually gets a little bit more complex than that. So the ideal way to use AWS Fargate and to build a SaaS is to make use of event-driven and asynchronous work. So what do I mean by that? Well, once again, as long as you're running a container, there's a flat cost for that container as long as it is running, even if it has no work to do. So if you spin up a container and it's serving 0 requests per second, you're still paying for it. However, with AWS Fargate, you stop paying the moment the container stops. So is there a way that you can take the work that you're doing and batch it up into batches where you do work and then you stop doing work? And as when you stop doing work, you stop paying. Now, there is some complexity to this because AWS Fargate does have startup latency. This latency has gotten lower and lower over time. It will continue to get lower. You can look at like Lambda, for example, as an example of how startup latency has reduced dramatically over the years. With AWS Fargate, there is a startup latency, generally about 30 seconds. But after it starts up, it's able to do an incredible amount of work using the full resources of the CPU core that is available to it. And then once you've churned through all this work, you can shut it down and stop paying for it. So consider whether there are certain parts of the SaaS which can be done asynchronously and queued up such that you can spin up the infrastructure, churn through that backlog of tasks that are queued up, and then turn off your infrastructure and wait for a backlog to build up again. And so this can be a pretty cool way to optimize your SaaS to save money. And it generally doesn't impact customers very much unless this is a software as a service, which has very tight SLAs on the time to get a job done. There's usually in any sufficiently large SaaS some pieces of the infrastructure which can be delayed, and customers are okay with you tell them, I'll email you a link in 10 minutes, or this job may take 5 to 10 minutes to do. It's generally because they are batching up work in the background and waiting until there's enough work to efficiently use infrastructure for the duration that they use it. I want to talk AWS Fargate specific about some of the ways to reduce your costs. And these are flat reductions. No matter how you make use of your infrastructure, these flat reductions apply based on the class of capacity that you're consuming. So x86 Intel-based processors, they're sort of the standard, they're what we've used for many, many years. But definitely consider using Graviton ARM-based processors because they are not only faster, but they're actually cheaper as well. So here you see the Graviton base price and then the Graviton price performance price. And so the reason why the price performance is actually lower than the price is because that this Graviton core actually gets more work done on the core compared to the Intel processor. And this is because of hyperthreading. With Graviton, you get the full power of a core, whereas with the Intel, what you're buying as a vCPU is actually hyperthread, or in most cases, half of a core. So price performance is lower per Graviton core whenever you buy a core through AWS Fargate. And then also Spot. So Spot is a provisioning model where there's a ton of capacity, and there's usually a fair amount of spare capacity inside of an AWS data center. It's sitting there in case there is a burst of capacity, and we would like to sell it to someone. We would like someone to make use of it so that it's not sitting there empty. And so we offer it as spot capacity. Now this capacity could be reclaimed from you at any time that it's needed. So if another customer, for example, has a big burst of on-demand task launches, the spot would be reclaimed in order to serve the on-demand. But what this allows you to do is launch way more tasks at a lower price performance. And so, for example, the standard rates from what I've seen for AWS Fargate allow you to launch 3 additional spot tasks for the price that it would take to launch 1 additional on-demand task. So here's how that might work. With Amazon ECS, there is a concept built in called a capacity provider, and you can provision your service to make use of not just one capacity provider, but multiple capacity providers as a capacity provider distribution strategy. And so here I've set up a strategy that says, I would like, as I scale out, for 2 tasks to be launched on AWS Fargate on demand, and then 4 tasks to be launched on AWS Fargate Spot. And so here you can see as I scaled up from 1 to 6 tasks, it's distributed 2 of the tasks onto on demand and 4 tasks onto Spot. Now the reason why I might consider doing this is that I always want to be able to serve the baseline needs of my SaaS tenants. And I've decided that the baseline needs of those SaaS tenants requires for there to always be at least 2 tasks running. However, I want to improve this quality of my service. I want lower latency for these customers. I want for there to be some extra capacity running in the background in case one of my customers decides to burst the number of requests that they're sending to me, or some extra spare capacity in case there's a bug in my application code and some of my containers actually crash for some reason and have to restart. I want to be running some spare capacity. Now the cool thing here is because I'm using Spot to provide that extra capacity, I've been able to run actually 6 tasks for the price of a little bit more than like 3 tasks, because those 4 tasks don't cost anywhere near as much as the on-demand tasks. And they could be reclaimed at any moment. It doesn't happen like super often, but it does happen sometimes. And when it happens, I'll still be able to serve all of the base traffic that my SaaS customers require. So I'm not going to be losing trust with anybody. They might notice slightly slower responses from loading web pages or from making API requests, but they wouldn't see any downtime. And so this is super important as a model to consider how you could guarantee that you have a lot of extra capacity at a greatly reduced price. So let's summarize. Let's summarize the different pillars and tips for each pillar on how to keep a SaaS running with Amazon ECS and AWS Fargate. So first of all, availability. Important things to know is that AWS Fargate isolates containers from each other to mitigate the impact of any spikes or things that are going on in one container. And it also makes it very easy with Amazon ECS to isolate different code deployments from each other. Additionally, Amazon ECS allows you to implement these zero downtime rollouts, as well as fast and accurate rollbacks with circuit breakers. So this is going to all work together to help you to build a system that is highly isolated and highly safe as you make changes to it so that your availability doesn't go down. Security. AWS Fargate is giving all of your tasks their own network interfaces, and they're allowing you to build these really detailed graph of network access between all of your tasks. And then it also allows you to create auto-rotating credentials that are unique to each container, but consider going down a level below that. Scope the IAM credentials that you're using down to individual tenants so that those tenants can't accidentally fetch data that they're not allowed to. And then the last two pillars are agility and pricing. So for agility, AWS Fargate simplifies the operational overhead by handling a lot of that for you. And it also is a serverless, versionless orchestrator, so there's never any upgrades or patches necessary. So you would compare this to something like Kubernetes, where there's new major versions of Kubernetes coming out on the regular. Now, I will say that there's something new that has launched, which is the EKS automatic mode. So definitely check that out. That is an interesting offering that I do like, and I do think will make Kubernetes more capable of the same agility that Amazon ECS and AWS Fargate has had for many years already. And then last but not least, the pricing model. This is how we keep our service from going out of business, on the infrastructure side at least. And that is that AWS Fargate can help you avoid wasting EC2 capacity, and it's going to offer multiple different cost-saving strategies that you can use to reduce the cost of your infrastructure. So that's it for me today. Those are the 4 pillars and the tips that I have for them. Hopefully some of this has helped you. And if you have any questions, feel free to come up and ask me.